my goal today is I'll be talking about applied climate science and risk assessment. My main goal for the talk today is to provide a solid basis for how to integrate climate change projections into your work as engineers, and to touch a little bit on what I do in climate risk assessment. So before I get into it too far, I'll just present a little bit about me. I'm a climate risk engineer, as Jack mentioned. I work for Stantec on the climate risk resilience and sustainability team. And I think the most important thing to note is that I'm not a climate scientist. My training is as a geological engineer. I've got a Bachelor of Applied Science, and then went back and did my master's in hydrology. And so a lot of what I've been doing recently is bridging that gap between geotechnical and geological engineering and climate science. So another note I'd like to bring up right before I get into it is a lot of the content that I'll be presenting today is based on work from my colleagues and their colleagues. But if you're interested in learning more, for sure would recommend checking out some of the courses offered by the Climate Risk Institute. There's really good content out there that there's some really smart people working on that are trying to open up the field of applied climate science for engineers across Canada. So to begin with, I want to just start with a quick little intro on the difference between weather and climate, because this is something that really gets tangled up in a lot of people's heads sometimes. And the best way that I like to explain it is that weather is short term, and it's kind of what you wear today. You look out the window and say, okay, I'm going to wear a jacket because it's dumping snow, much like yesterday in Calgary. Whereas climate is what's in your closet. It's what you expect to happen. You're not going to own a big thick parka if you live in Hawaii, for example. So climate is short term, and it can change rapidly, spatially and temporally. On the other hand, climate is looking at gradual progressions and long-term changes, and it includes a much wider area. That's just a really quick summary of the difference between weather and climate, but I want to motivate the talk about it as it relates to climate change. So when we talk about climate, what we really mean is the long-term distribution of weather. And for our purposes, we can think of weather as just temperature and precipitation. I mean, of course, there's plenty of other elements, but those are the main ones that we concern ourselves with. So what this graph is showing is that with climate change, we have a shift in the probability distribution of those variables. So here we're looking at temperature, but it doesn't necessarily need to be that. It could also be precipitation. So not only do we have a shift in the mean temperature over time, but more importantly, well, arguably more importantly, you also have a shift in the tail end of those distributions. So that bright red section on the right-hand side of the figure, you've got more record hot weather. And that's sort of the tail of the graph. And that represents those extreme events that we've seen a lot of over the past couple of years. So events similar to the BC floods that we saw back in November. There's been a lot of different events similar to this, obviously very impactful, very much related to climate. And just because of the fact that we had that huge atmospheric river that came in. I think there was a really great talk a couple of weeks ago from Carrie Ann and Matt Lotto through this Calgary Geotechnical lecture series. Also, there's massive floods in Australia only a couple of weeks ago. I think for some projections, we're calling it a 1 in 1,000 year flood. Obviously, with climate change, it's really hard to tell what is a 1 in 1,000 year flood at this point. But also things not necessarily just precipitation related, also heat related. There was the heat dome in BC last summer that wiped out the town of Lytton. Not only did they smash record temperatures, but they also ended up having a wildfire raise the entire town and effectively wipe it out. So this kind of all inspires the problem of climate change, but we want to know, how are we going to plan for this? So how do we plan for climate change, and how does that influence our work as engineers? One of the most important elements we have in design is in the building code. Here we're looking at the BC building code and the change of temperatures that it accounts for. So on the left-hand side is we're showing the temperature change, and on the x-axis is time from 1950s up to 2100. As you can see, we've reflected that building code. There's the sort of past building code that we had based on baseline temperatures, and we've changed that to account for the fact that we're seeing differences in temperatures. But as you can see, the temperature is continuously increasing. So we kind of have this moving target that we need to work with because climate is no longer stationary. And updating these codes is a huge logistical and administrative challenge that takes a long time to be implemented. So the question becomes, how do we account for this moving target and design for a changing climate? And that's really the question that I want to try to answer today. And I've included this cartoon on the right-hand side of this guy looking into his crystal ball to try and see what the future is going to look like. Sometimes that's how it feels when we're trying to get a sense of what future climate will look like. But luckily for us as engineers, there's a huge amount of scientific research out in this field to help guide us along in implementing climate risk assessments. So the three main questions I want to answer today is, how can we estimate what the future climate will look like? And the answer being, we're going to use the results from global climate models. Another one, how can we apply climate model data? Once we have those climate models, what do we do with it? And there's a few different techniques that we use in order to better understand and make sense of those climate model outputs. It's called downscaling. We can ensemble the data and we can use climate model indices. And lastly, how do we actually decide what to do about it? So I want to touch on a little bit of what specifically climate risk assessment looks like and what are some of the tools that we use to conduct that and plan for it, including engagement and adaptation. So let's kick it off with a discussion of climate models. What are they? How do they work? And why should we trust them? Climate models at their core are basically just computer programs that are designed to simulate future weather conditions. On the left-hand side here, we're looking at a sort of cartoon of what climate models can do. So you can think of these as a whole bunch of different modules that are sort of packaged together. It's much like any sort of slope stability model you might use, but instead of just looking at the particular slope or domain that you're interested in, we're looking at the entire globe surface, and we're looking at the atmosphere, the hydrosphere, we're looking at forests and interactions between the sun and solar radiation. We're looking at cloud formation. There's a ton of different elements that go into these programs. But one of the most important ones that we want to really understand is how the impact of changes in atmospheric composition, so that's the release of greenhouse gases, are going to influence the climate of the future. So we have all these sort of like little chunks we have these programs that are designed to simulate what the global future is going to look like. And in order to put that into a computer, we need to put it onto a grid. So on the right-hand side here, we're looking at basically what a climate model grid looks like. It's all the way across the world. The grid cells are about 1 degree in size. So that equates to about 100-kilometer grid cells. And then they're 3-dimensional. So we're also looking at exchange vertically throughout the atmosphere. So that's very generally speaking what the climate model does, but these things have kind of evolved over a long period of time. The first climate models that were released were in the 60s, and they're quite simple. It was just an exchange between the atmosphere and the ocean, simulating how those interactions are going to look. And it was really just based on a few different researchers. Through time, there's been more of these modules added on to climate models. So they're getting more complex and integrating a lot more physics and complex physical interactions between different elements that we weren't able to see before. So they're continuously getting better and more accurate with time as more people are working on these problems. And not only are we adding more modules, but there's also more players in the game. There's more people and for the most part, academics and researchers developing these models that are kind of coming at the problem from independent approaches. So they're developing completely different models based on the same physics, based on the same planet and climate that we're looking at in order to understand how that's going to change in the future. So in the 90s, you can see that was when one of the first IPCC reports came out. We were looking at about 11 models from 11 different researchers. And most recently, the IPCC report that came out in 2021 had about 42 different models that had been released at the time. And I think we're projected to get about 100 or so more models, 100 or so models by the end of the completion of this sort of round of modeling. So who are the people who are producing these data? For the most part, it's researchers from institutions across the world. There's a whole bunch in the US, a few in Canada, Europe, Asia, Africa, Australia. But really what the most important thing to note here is that it is sort of a combined effort. Everybody's sort of teamed up together, and that's through what we call the Coupled Model Intercomparison Project, often shorthand referred to as CMIP, CMIP 5 or CMIP 6. CMIP 6 is the most recent round of models that came out with the latest IPCC report. So what CMIP does is it provides a standardized framework for climate model experiments. It standardizes the model grid size and shape. It allows us to make sure that it allows us to compare apples to apples when you're looking at the performance of different models. Probably the most important thing to realize with CMIP, and one of the greatest benefits of having this intercomparison project, is it allows us to compare the same greenhouse gas emission scenarios across a variety of different models to understand what are the possible outcomes from that. And from a more practical perspective, I can just knock my camera over. From a more practical perspective, this project actually allows us to provide a standardized data format to make it easier to access and work with a lot of different climate models. So now all of a sudden you can work with a whole bunch of different climate models because of the fact that they're all centralized in one place and they're all in the same format, for example. So you can actually get at this data a lot more easily because of this organization. So what do climate model outputs look like? It's all well and good to understand that there's these great projections of future climate, but to answer the question of what to do with it, we also need to understand what they actually produce. So what do those outputs look like? Here I've grabbed the output from 12 or so climate models at one particular grid point for a slice of time between about 2022 and 2025. And we're looking at mean daily air temperature. So that's one of the outputs that they provide. They also provide precipitation, wind speed, air pressure, and a whole bunch of different variables that climate scientists are really interested in. But for my work anyways, as a climate risks engineer, we mostly only look at temperature, precipitation, and sometimes wind. As you can see, each of these colored lines is simulating what the future weather conditions might look like. And what we want to do is, you can see that there's a ton of uncertainty there. I mean, on any particular day, it could range from 0 to 20, which is actually kind of a good thing because we recognize that the weather does vary that much. We want to know what is the range of distributions that are likely in the future. So really what these climate model outputs are providing is plausible future weather conditions. And it's also important to note that typically climate models run from about 1950 to 2100. And so here you can see they run independently. They don't actually account for measurements that we've made in the past 50 or 60 or 70 years, but they seem to replicate them fairly effectively because of the fact that they're sort of trained on them. And here what we're looking at is sort of like the wider scope or the wider range of climate model outputs. So here we're looking at temperature anomaly from 1980 or so to 2050. And you can see historically, the black line is what we've observed. The gray lines are showing what those climate models simulated in the past. So you can see that the model simulations agree fairly well with the observations. And then moving forward, we need to account for these changing greenhouse gas conditions. So that's where the colored lines come in. Depending on the color, those are the different greenhouse gas contributions to the atmosphere that may impact future climate. So there's a huge swath of scenarios that could happen here. And one of the important things to realize when you're working with climate data is what are the sources of uncertainty and how do we sort of control for them and understand them in order to make scientifically justifiable decisions about that data. So the first thing to note is there are three main sources, I should say, of uncertainty. On the left-hand side, we're kind of looking at the same graph we're just looking at here, but in this case, we've simplified it to highlight the area, the zones or spread of uncertainty, depending on where it's coming from. So in the orange, we're looking at the internal variability. So that's the variability of climate as within a model. So how much does it change? It's really just noise within the model, which is actually, once again, it's a good thing. I mean, it's something that shows that we don't actually know what the weather is going to look like every day. And so we want that little spread of how much uncertainty is there in the weather from a day-to-day basis. The second major source of uncertainty is in model spread. So from one model to the next, there's increasing changes over time. So if I look at one model, it's going to, maybe it's weakly biased, warmly biased, I should say. And so it's going to gradually sort of increase in temperature over time. Whereas on another model, maybe it's cold biased. So that will gradually decrease temperatures over time. It could be a result of the model grid size, or it could be a result of just the way the physics are coded. But we really don't have a great sense of why each model is biased, but what we can control for it. Lastly, there's also, and probably the most important source of uncertainty is in the scenarios. So this doesn't actually necessarily have to do with the way that the model itself is performing, but it relates to what are the assumptions that are going into the model. So you've probably heard of things called RCPs or SSPs, and these are basically scenarios that project what the future greenhouse gas emissions assumptions might look like. So oftentimes those scenarios will spread rapidly because of the fact that we have a lot of feedbacks in the Earth's climate system. So the more greenhouse gas you're pumping into the atmosphere, the more likely it is to have increased warming over time. So coming back to that scenario uncertainty, let's talk a little bit more about RCPs and SSPs. RCPs are really just the old version of SSPs. They're not quite they don't quite replace, or SSPs don't quite replace RCPs. However, the two are kind of complementary and they work off of each other. At their core, they're just providing a framework for us to sort of standardize what are possible future outcomes in terms of humans' behavior in order to understand what that behavior is going to look like on the climate. So RCPs are referred to representative concentration pathways, and they were used in the CMIP-5 model experiments, which were released in 2013. And they're based on different greenhouse gas emissions assumptions, ranging from 2.6, which is quite low, and I think it's effectively been ruled out at this point, to about 8.5, which is a high emissions, or you may have heard of it as sort of the business as usual scenario. On the other hand, the SSPs refer to shared socioeconomic pathways, and these were released as part of the IPCC report in 2021 that came out, and they were used in the CMIP-6 climate models. And what these do is, rather than just looking at greenhouse gas assumptions, they're based on socioeconomic trends. So it tries to simulate how we behave as a global civilization to understand what that impact is going to be on the climate. So they range from 1, which is sort of equivalent to the low emission scenario, and what that refers to is wide sustainability and equity across the planet, versus SSP5, which is unconstrained growth. So we're just continuously growing and pumping emissions into the atmosphere. As you can see on the right-hand side, RCPs and SSPs are related, as I mentioned, but they're not quite the same. Okay, so that's one source of uncertainty, but let's talk also about model uncertainty. Why are models biased? One of the main reasons that models are biased is because of the fact that there's limited spatial resolution. Of course, we don't have infinite computational power, and these climate models are really complex. So we need to use fairly large grid sizes. We've got really large grid cells, and therefore we need to simplify the physics that interact between those grid cells. Obviously, if you've got a mountain or an ocean nearby, that's going to impact the climate, but that climate is not going to be necessarily reflected within the climate model. On top of that, there's also the fact that models don't necessarily we don't have a perfect understanding of the Earth's climate system. Of course, we don't quite understand every single physical exchange out there, and that's kind of why we're continuously working on these things in order to improve the performance of climate models. So very generally speaking, just to get a sense of what model bias looks like, on the left-hand side, this is what a global climate model output would look like. We're looking at the mean surface temperature that's projected across the entire planet. And on the right-hand side, this is the mean model bias. So this is how far off that simulation is from the temperature or the recorded temperature in the historical period. So you can see, for example, on the west coast of South America, it's got a warm bias. So that model is producing warmer temperatures than we would typically expect. The good thing about bias correction is that you can correct for it based on these historical temperatures. So if you run your climate model in the historical period without sort of telling it about the measurements that you've made, you can compare it with those measurements in order to correct it. I'm just going to try to illustrate that here. What we've got here on the right-hand side is your climate model output. So we've got the model temperature in the past and the model temperature in the future, and those are based on the model that was produced and based on physics and all the science that we've put into these things. But we really want to know, excuse me, the real temperature in the future. We don't really care about the model temperature if we know it's wrong. So what can we do? We can look at the real temperature in the past and compare it with the modeled temperature in the past in order to identify, okay, this model seems to think that the west coast of South America, for example, is a little bit warmer. So what we can do is we can difference those things in order to correct that future projection of modeled climate in order to produce a bias corrected temperature. And so once again, these are estimated projections of future temperature, but it does improve that model bias by correcting it to measurements that we've made on the ground. And I'm not going to get into all the different ways that you can do this bias correction because there's really complex approaches. There's also really simple approaches, but some of the main methods to be aware of and just to sort of like be able to speak the language are called delta change, change factor, and quantile mapping. I won't get into them, but if you're interested in these types of things, feel free to just sort of note those down and dig into them further. So that kind of brings us to the end of what climate scientists produce, apart from one other thing, but I'll bring that up in a second. But the next question is, okay, we've got these climate model outputs. How do we make sense of them? Climate scientists are providing us with these increasingly large databases of projection data, but they don't always include the information we need. We've got maybe temperature, we've got precipitation, but we have to sort of take the data the sort of last mile, as they say, in order to deliver it and make some decisions about what to do about it. So how can climate model outputs be used for engineering analyses? Things like looking at the impact on roads or on houses or whether I can fry an egg in a pan, that sort of thing, important questions that need to be answered. One of the biggest limitations of climate models, as you've probably picked up already, is the fact that they're at 100 kilometers grid scale. They're quite coarse. So one of the tools that we use to account for this is called downscaling. Downscaling is the process by which coarse resolution climate models outputs are translated into a finer resolution, into the scale of about 10 kilometers or so. They can get down to about 1 at some times, but typically they'll get downscaled to about a 10-kilometer resolution. So on the left-hand side, you can see we've got this really sort of patchy, gridded climate output of temperature. And on the right-hand side, once we've downscaled it, it produces a lot more of a realistic, or what we would temperatures that we are more likely to expect in reality. And there's two main approaches to downscaling. The first one is called dynamical, and the second one is called statistical. Statistical downscaling, put simply, is interpolating climate model outputs. There I put the acronym GCM. Oftentimes, climate models are referred to as general circulation models or global climate models. Doesn't really matter at the end of the day. Most of the time, people just call them climate models or GCMs. So back to what I was trying to talk about here, which is statistical downscaling. What they're doing here is they're interpolating those GCM outputs in order to produce a finer resolution climate projection. So you can use all kinds of different predictors. I mean, you can literally just interpolate between A and B spatially, or you can account for things like elevation or past measured temperature or pressure or land use, that kind of thing, or proximity to the ocean. You can use any one of these sort of predictors in order to produce a statistical model to produce a higher resolution climate model output. On the other hand, we also have dynamical downscaling, and dynamical downscaling is producing high resolution, is basically conducted by high resolution regional climate models. So we refer to those as RCMs over a smaller area. So you have the GCM, which simulates the entire planet. And then the RCM says, okay, let's just look at the climate within Europe so that we can actually run it on our computers and use a finer grid cell. Typically, the GCM outputs are used as a boundary condition for the regional climate models. And typical resolution for regional climate models is about tens of kilometers. So still not on the scale that we'd love it to be, but some of them can provide information at about a kilometer grid scale. Obviously, when we're producing these outputs, you kind of have to account for the fact that regional climate models are almost equally as complex as global climate models. However, they're at a higher resolution. So they're really hard to produce and hard to execute because of the computational demands, but they do provide a more physically realistic output. Another important organization or sort of initiative to be aware of is called CORDEX. I won't even attempt to remember what the acronym stands for, but it's very much like CMIP, but for regional climate models. So in much the same way that we sort of have this organization that standardizes the way that we run global climate models, there's also an organization that says, okay, let's produce regional climate models just for North America. You can see that there's that box around North America. And then they standardize the way that those outputs are saved, produced, and output and stored for our access in order to provide a little bit higher resolution than you might otherwise get from a global climate model. So there's these two types of downscaling in order to produce higher resolution outputs. Statistical, which is really computationally efficient, but not necessarily as physically realistic. And on the other hand, you've got dynamical climate models, which are more physically realistic, but difficult to run, computationally not particularly efficient. And so we really have to work with the balance of which one do you like more, or would you prefer to work with? Both are good. There's no real right answer here. Coming back to applying climate data, another way that we sort of take those climate model outputs and make some sense of them is by using model ensembles. And you've probably thought of this already, and I've alluded to it earlier in the presentation, but the whole premise here is we have these 40 or 100 or who knows how many climate model outputs, and let's take all of those and better understand the distribution of likely climate conditions. So the whole premise is with a greater number of climate models, that'll bring us closer to the truth, quote unquote, and help us understand the likely range of the future climate. So here on this graph, we're looking at the projection of number of hot days over time. So running from 1950 to 2100, as I mentioned, that's how the typical timescale of most climate models. So you can see here, the red shows a whole bunch of different individual climate model outputs. So that's temperature on every single day, much like we saw earlier. However, this time what we've done is we're taking the mean. We're going to look at, okay, what's the mean of those 40 different climate models, and how does that, and therefore we can have a little bit more confidence if we have 40 different simulations producing a very similar thing. The mean is going to bring us closer to what we think will be the truth. And the other benefit of using an ensemble is you can also get a sense of that distribution. So you can take the 10th percentile of those models or the 90th percentile and have a good idea of the likely range of future climate based on the particular simulation that you're looking at. So whether that be RCP 8.5 or SSP 5, for example, you'll have a good idea of the distribution there. Another thing that we like to do with climate data is divide it into periods. So as I mentioned, the climate models produce effectively they simulate what effectively they think will be the weather on any given day. We don't take that to be correct, of course. What we do is we aggregate those simulations over across a bunch of different models, as I just mentioned in the previous slide, and also over wider timeframes. So we don't necessarily think the projection for June 17th, 2047 is going to be correct. What we do is we look at 30-year periods, and this is typically the timeframes that are used in applied climate science, at least. But there are, you can kind of split it the way you want. Typical convention is that we look at the baseline period, which runs from 1980 to about 2010. So before we had really major impacts of climate change on our measurements. And then we break that also out into the final 90 years of the 2000s in 30-year chunks. So we're looking at the 2020s, 2050s, and 2080s. Of course, you can always change these climate periods depending on what your application is. You don't need to do 30-year periods. That's typically expected, but it doesn't, you could break it into 10-year chunks depending on what sort of life cycle you're looking at for your asset, or if you're have a particular planning horizon, maybe you only have a building that's supposed to last for 30 years. You really don't need to be planning out to 2100. This one is one of, if you take nothing else away from this talk today, I think this is probably one of the most important elements to recognize, and that is climate extremes indices. What this is breaking down that complex climate model output, so temperature and precipitation, into more practical indices that we can really understand. So things like the number of freeze-thaw cycles. You can grab an index from the climate model based on how many times is that temperature, the minimum temperature over the day below zero and the maximum temperature above zero. That'll give you the projected number of freeze-thaw cycles. And then we can start to use that information to make decisions about how we're designing. Another example is the number of rainy days that we have. So how many times is it going to rain more than 20 millimeters? Maybe that impacts the number of landslides that are going to occur on the slope that I'm working on. There's a bunch of standardized extreme indices developed by the expert team on climate change detection and indices. And they're offered by a lot of different climate data providers. There's also a few different websites you can go. This one I put on the slide here is called ClimPact, but there's also one called ClimDex. And what these do is provide a whole bunch of climate indices for you to make sense of the climate data in the form of things like freeze-thaw cycles or rainy days. And on top of that, you can also produce your own extreme indices. So you don't necessarily need to use the ones that have been produced by the expert team, depending on the problem that you need to solve. So for example, I had a recent project that wanted to know about flash freezing. And with the way the client described this event was they said that we have a really hard time dealing with the fact that dealing with snow removal when it comes down really wet and then the temperature drops shortly thereafter because the snow just solidifies like concrete and there's no way to get rid of it. So they end up having some huge problems in terms of access to their site. So therefore, you can imagine a situation where you've got the climate model outputs. How often do we expect wet snowfalls? So when the temperature's around 0 or 1 degrees sort of thing, followed by a rapid temperature drop. There's your index. Say annually, we're getting about 5 of them. Then in the future, what is that number going to look like? So that allows you to make some decisions about how should we be planning to account for these climate changes in the future. Another one that I've kind of played around with just out of interest is looking at ski resort powder days. So this graph I'm showing here is the projected number of powder days for a particular ski resort per winter from 1960 to 2100. So as you can see, the 2 different model scenarios, we've got RCP 2.6 and RCP 8.5. That's the business as usual high emission scenario. Initially in the 60s and 80s, we're looking at a pretty similar amount of powder days expected. So you can imagine a powder day you can define as, okay, when the snow falls, but it's still cold, so it's nice and light and fluffy. But we also want enough of it. So we need it to be greater than 10 or 15 centimeters, for example. So it's got to exceed a threshold depth. As you can see, the powder days at this particular resort are projected to decrease. So that allows, I mean, I haven't done this for a real project, but I can imagine it would allow a ski resort to start planning for the fact that, okay, you're not going to have as great of ski conditions in the future. What are you going to do about that? What's the next step? As I mentioned, there's a whole bunch of different data sources that produce these climate model that provide these climate model outputs. Specifically in Canada, we've got 3 really, really great websites. My favorite is climatedata.ca on the left-hand side, but also the Canadian Climate Atlas is really helpful, as well as the PCIC Climate Explorer. All of these 3 of these websites use the same underlying data set. It's referred to as CAN-DCS from PCIC. And what they're producing is they're statistically downscaling. Remember what that means? 10 down to about a resolution of about 10 kilometers across Canada. And they're also bias correcting those models so that we know that they do match with the observations that we've seen, and ensembling them together in order to produce a realistic distribution of climate model outputs that we might expect. So 3 really, really great resources for the Canadian environment, at least, and the US also has a lot of really good ones. But internationally speaking, there's the Copernicus Climate Data Store there, where you can go and download directly the outputs from global climate models. You can produce them as CSVs or raster files, and things that you can just bring directly into your workflow to better understand what the future climate's going to look like. On top of that, there's the IPCC Interactive Atlas, really, really helpful. And you can click around. Not only are these resources valuable as data sources, but also as learning resources. There's a ton of money and energy getting poured into these things to really express climate science and to increase education amongst practitioners, especially. So I would really highly recommend checking these things out, even if you're not going to use them on a project, just to sort of educate yourself if you're interested in the topic. Okay, so we've covered what climate models are and how we sort of how we apply those outputs to practical situations, but how do we decide what to do about it once we produce estimates of climate risk? Or sorry, once we're working with that climate data, once we've got it, how do we decide what to do about it? How do we prioritize our next step? And I want to just give a quick plug for the PyVC protocol, because this is a lot of the basis for which I'm going to present the next couple slides here. The PyVC protocol is a risk screening tool developed by Engineers Canada. It's not particularly complicated. It's basically just a workflow for conducting climate change risk assessments. You've probably worked with very similar structures before, but it just provides a formalized process that allows you to work through providing a climate risk assessment. And the reason I've sort of highlighted step 3 in the PyVC workflow here is because of the fact that it's important to note that in my work, at least as a climate risk engineer, we kind of sit at a higher level. We don't really conduct those detailed engineering analyses of risk assessments. We're trying to view a broad scope of hazards and provide a relative risk score, as opposed to providing really detailed engineering analyses, which are the kinds of things that you can conduct once you've prioritized, okay, which are the important hazards to consider? Let's dig into those deeper. So you've probably seen graphs that look a lot like this in the past, looking at how to produce a risk assessment. It starts with hazards and assets, hazards being things like flood, fire, landslide, assets being what you care about. So whether it's a mine or buildings or roads or railways, and how do we go from those elements to a risk score? So we need to translate that hazard into a probability. We need to know whether it's impacting the asset, and we need to know what are the consequences of what would happen if that asset were impacted by a particular hazard. And then at the end of the day, what we do is we multiply those 3 factors together to produce a risk score. So I'll walk through each of these elements in a little bit more detail in the next slides. Starting with climate hazards. A climate hazard is a physical process or event driven by climate that can cause harm to assets. Pretty straightforward, but the most important thing to note is that it's not necessarily a rigid list. There can be chronic or acute hazards, so things that are sort of pile up slowly over time, impacting your assets, things like sea level rise or drought or warmer temperatures just in general. Maybe that'll push some tree species out of the ecosystem. And on the other hand, we also have acute hazards. So things like heat waves or river floods or hurricanes or landslides. Those are the examples of hazards that occur over a very short period of time that can impact your assets. Really important thing to note is that there's a lot of hazards that are typically sort of lumped in with climate risk assessment that are not necessarily climate hazards, specifically earthquake, tsunami, volcano. Those types of things are more geophysical as opposed to being climate related. Also, of course, there's human related hazards that sometimes we need to account for when we're doing risk assessments, things like pandemics, cyber attacks, terrorism, that sort of stuff. But when we're trying to get a sense of climate hazards, there's obviously a lot of uncertainty in how those hazards are going to change in the future because of the fact that we're using climate models. So climate models are more effective at long-term, large-scale weather systems and storms, whereas on the other hand, they're not really that great at resolving really high-resolution events because maybe in 100 years of simulation, you only get 1 or 2 100-year events that are going to actually occur. So that's 1% annual exceedance probability. So there's less certainty in the magnitude and spatial distribution of those acute hazards. On the other hand, so we have more certainty in things like temperature, that will have warmer winters, longer growing seasons, more heat waves, and less certainty in things like wind. Climate models are not particularly good at simulating wind. A lot of the reason for that is because of that really coarse grid scale. So we need to account for the fact that there's quite a bit of uncertainty in those climate models and carry that through into our hazard likelihood assessment. So there's a lot of different ways of calculating or estimating the probability of a hazard. And I'm sure a lot of you are familiar with them based on your work. And most are empirically derived based on real world observations, things like flood frequency analysis, IDF curves, landslide FM curves, things like that we use to simulate, okay, what are the projected magnitudes and frequencies of these particular events we're interested in. However, we know that the climate isn't stationary. This is a graph of temperatures over the past 1,000 years. And as you can see, the climate is not stationary anymore. So it's really hard to rely on those historical measurements in order to understand what the likelihood of the hazard is going to be in the future, because those measurements aren't necessarily still valid in order to project forward. So what we do is we use climate model projections to estimate the frequency of climatic events. And you can refer to events as indices, things like heavy rainfall, as I mentioned, heat waves. How many days per year do you expect 5 days in a row when it's 35 degrees or higher? Also, things like ski powder days. We can look at what the ski conditions are going to look like in the next 50 to 60 or even 80 years. So on the right-hand side here, we're looking at the number of extremely hot days. How many are we projected to get in this particular location when the temperature is greater than 35 degrees? Next, what we do is we take that hazard sort of probability and the estimate of the probability of that hazard and translate that into a likelihood. Don't even try to read this slide. The most important thing to recognize is that there's 2 different approaches to hazard probability. On the left-hand side, there's that sort of absolute probability, and you can translate that into a likelihood score or a relative probability. So absolute being the type of thing that you'd use for an acute event that only happens once in a while, things like a flood, for example. And then you can bin those probabilities into relative risk scores. Typically, we try to keep these bins wide because of the fact that there's a lot of uncertainty in the likelihood projection. So therefore, we try to keep those bins wide so that we know, so that we're really expressing the level of uncertainty in that analysis. On the right-hand side is a sort of a different approach. This is what you'd use for things like a chronic hazard. So if you're looking at what is the projected likelihood of freeze-thaw events, obviously you still get 60 freeze-thaw events or so per year, but how is that going to change on a relative basis? So another way of producing a likelihood score for this is to sort of say, okay, well, currently we'll call it a 3, and then how is that going to increase as a relative percentage? And you can provide a likelihood score that way. Next step is to look at the assets that you're interested in. And an asset is any physical entity or process that delivers value to users or owners. So they can be aggregated in any number of groups or broken down into individual elements. One of the most important things is that it requires engagement with stakeholders, local operations staff, and other experts, especially as a climate risk engineer. A lot of what my job is to engage with the people at these sites to say, hey, what are the assets that are really important to make sure that your operation is still running? Once we've done that, we can also look at what is the asset life cycle. Does climate change actually matter over the next 50 to 100 years if your building or your Your streetlights, for example, are only designed to last for the next 5 to 10 years. Maybe you don't even need a climate risk assessment. So the next step is once we have our asset exposures, once we have our assets and our climate hazard likelihoods, we get into exposure and impacts. So does the hazard interact with the asset? Typically, this is expressed as a number of 0 to 1, and it means that we're overlaying those, for example, something like a flood map. You overlay that on top of the hazard, or on top of the asset, and say, yes, there is an impact of this threshold flood that I've decided is important for this asset upon this particular location. And once we know whether an asset is exposed to a hazard or not, then we need to start talking about the impacts. Okay, this building is going to be exposed to a flood, but is it going to be impacted? And how is it going to be impacted? Because that's the way that we sort of take the next step to identify the consequences. Impact statements are really just used to constrain the likelihood analysis and identify the way in which assets are affected by hazards. Of course, a flood could impact a building in any number of ways. It's really hard to constrain that. So what we do is we trim that down into a concise statement that says the building is impacted by flood based on, let's say, inundation and is destroying the walls or causing it to mold to form and rot out from inside. So that's an example of an impact statement for a building that is exposed to flood. On top of that, we could have things like freeze-thaw events. Freeze-thaw events cause crack formation in pavement. It's a really simple impact statement that sort of ties the hazard to the asset and allows you to take the next step in the analysis, which is to produce a consequence score. And a consequence is typically a typically adverse outcome that may occur when an asset is exposed to and impacted by a hazard event. So to answer the question of what would happen if this flood impacted this building, and this takes a lot of creativity and it takes a lot of engagement once again. So we need to speak with those people who know about these assets in order to understand what is going to happen to that asset once the hazard impacts it. And once again, we try to aggregate these scores into a wide range of bins, bins with wide ranges, sort of on the order of magnitude type of thing, specific to the application. So if you're interested in the impacts on humans, you can sort of break those bins into things like a first aid injury being 1 versus a fatality being a score of 5. And these are typically catered to each project. What you will do is we'll go in and say, okay, what are the consequence criteria that matter to your organization and assets? On the other hand, there's also economic consequences. So you kind of have to break it out that way. So you're going to have an entirely different risk score as it relates to the economic consequences as compared to the human consequences. So economic consequences, it could be, okay, maybe we can handle this damage because of the fact that it's within our operating budget. It's only going to cost us $1,000 to fix. Whereas if we have an entire factory wiped out sort of thing, then that would be devastating to the organization. That's a 5 on the economic consequences scale. So when we're producing our climate risk assessment, coming back to that sort of figure, we've talked about what a hazard is, what an asset is, how we come up with probabilities or likelihood scores, whether the asset is exposed or not. So is that a 0 or a 1? What are the consequences if that asset is exposed? And then we multiply those together to produce a risk score. And I'm sure everybody's seen this one before. This is an example of a risk matrix, and I just want to use it to highlight how we decide what to do about climate risk assessments once they've been conducted. So imagine you have a flood in the current climate, relatively low likelihood, but highly catastrophic for a particular area or asset. With climate change, that's going to shift that probability into the red zone, the higher risk area. And next step is to say, okay, we know that that flood is going to be a higher risk asset. What are we going to do about it? So that's where the next step of climate risk assessment comes in, or sort of the way we sort of tie up and decide what to do next is called adaptation. And adaptation is typically reduces the consequences of impact because of the fact that we can't change the fact that the climate is changing, at least not on an organizational or individual scale. We're going to have to deal with the fact that it is happening in order to adapt, or at least it's important to account for the fact that we should be adapting to these changes in climate in order to reduce the consequences of an impact if a flood should occur. So the next steps, once we've produced these climate risk assessments, is to identify adaptation options to enhance the resilience of the organization or site or project. So adaptation is defined as the process of adjustment to actual or expected climate effects to moderate harm. And it's really important to tie out a term that climate scientists typically use, which is mitigation. And we also use it as geotechnical engineers. The term mitigation in the climate change context typically refers to mitigating the process of climate change specifically. So reducing emissions, that would be things like carbon removal techniques and things like that. That would be climate change mitigation. Instead, when we talk about the physical impacts of climate change, things like floods, landslides, etc., what we're talking about is adaptation and adjusting to those impacts in order to be resilient to climate change. Once again, one of the most important things for identifying adaptation options and increasing resilience is stakeholder engagement. It's really important to engage with the people who know the site, who know the historic damages that have occurred to the site and that sort of thing, in order to take the next step and identify what are the adaptation options we need to consider in order to produce a more resilient design for our site, asset, project, etc. So at the end of the day, the objective is resilience of the asset. And on the right-hand side, I've pulled this graph from the City of Vancouver's sea level rise management plan, and they lay it out really nicely as the 3 different sort of adaptation options. What we can do is there's one way to sort of resist that change, and we can continuously build dikes higher or seawalls higher in order to resist the impacts of sea level rise, or we can accept the fact that it's going to happen and let's start accommodating it with our design. Let's put our houses on stilts or make floating buildings and that sort of thing. And the last option, which is typically the most effective, and you hear a lot about in the media and from climate resilience professionals, is to just move out of the way. Obviously, if you're in a floodplain, the best way to reduce your risk to 0 is to move your house. So those are the 3 main approaches to conducting climate adaptation. So I just want to summarize real quick here. I know we're almost out of time. Hopefully we've got a few more minutes for questions, but just to summarize quickly, climate models are used to project the future global climate at a large scale, but the outcomes are uncertain and difficult to interpret. However, we can manage that uncertainty by looking at various different scenarios. We can bias correct those models. We can look at ensembles together in order to identify what is the distribution. We can break those out into temporal periods in order to understand what is the likely distribution in the future. We can make the results more useful by downscaling them to higher resolutions. We can go from that coarse grid scale to a more fine-grained grid scale that is more applicable to our particular site. And we can also use indices. We can query those climate models based on a specific criteria that's relevant to our project in order to make those results useful. And lastly, we can decide what to do about those hazards and risks once we've identified them, by conducting climate risk assessments and prioritizing them in order of the amount of risk posed to each asset. And lastly, of course, we want to identify those adaptive measures in order to reduce risk and increase resilience. So with that, I will hopefully have a little bit of time for questions. And thanks a lot to everyone for listening.